want to thank you for joining us today for this webinar on teaching about volcanoes with monitoring data and communicating risk. It's part of the NAGT webinar series, and the sponsoring project for this particular webinar is GEodesy Tools for Societal Issues. Before we get started in the actual webinar itself, I just want to make sure everyone's comfortable with the controls. If you move your cursor around, this black bar should appear at the bottom of your window. Please do make sure that your audio and video is muted so we don't cross contaminate the noise. You might want to have your participant window up to the side by clicking on here, and that'll allow you controls such as raise hand, yes, no, and things like that. You'll also probably want to have the chat box open so that you can ask us questions as we go along. We'll be trying to monitor that and catch things as they come. Let's see. Okay, there we go. So this is part of the National Association of Geoscience Teachers webinar series, which happens roughly weekly during the main part of the academic years. You can check the upcoming schedule by going to nagt.org website or see the archives where all the past ones are posted. And this is a collection of different webinars brought together by different geoscience teaching related and education related projects. Today, of course, we'll be talking about teaching about volcanoes with monitoring data and communicating the risk. You can feel free to go to the Getsy website and follow along. So that's just circ.carleton.edu/Getsy. If you're interested in actually looking at the module itself, you'll see it right there near the top under of the Getsy page there under the introductory modules. I am Beth Pratt-Sitola. I'm one of the PIs and project manager for the Getsy Project. I work for UNAVCO, which runs the geodetic facility for the National Science Foundation. And then a little later in the program, you'll hear from Katja Kraft, who's one of the authors of this module. Before that, I'll give you a quick overview of the Getsy Project and some of the details of the monitoring methods and the geodetic data sets. So what is Getsy? It is a project with a mission to develop and disseminate through webinars and short courses and things like that with instructors, teaching and learning materials that feature geodetic data and quantitative skills applied to critical societal issues such as climate change, water resources, and natural hazards. It's a sister project, a sub-collection within the Integrate project. Getsy has had 4 grants total, which has led to the development of 13 modules that are roughly 2 weeks each. There's both introductory and majors level modules, both classroom and field. This one, of course, is more oriented toward intro to middle level and classroom, this particular one today. To make sure we're all on the same page about what geodesy is, it's the science of accurately measuring the Earth's size, shape, orientation, mass distribution, and the variations with time. Traditional geodesy, it was just precise positioning of points on the surface of the Earth. You might think of it as simple surveying because 100 years ago, that was hard enough. But in the last few decades in particular, it has really blossomed into a toolbox of different ways to better measure the Earth and over different timescales. So if you want to unpack the geodesy toolbox, you will find things like GPS, Global Positioning System, InSAR, which gives you more regional deformation instead of point movements. Anything that's high resolution topography, such as might come from lidar, laser ranging, or photogrammetry, structure from motion photogrammetry, is considered part of geodesy, as are strain meters, creep meters, tilt meters, and other very sensitive instruments like that. There's gravity measurements, especially the GRACE gravity satellite, and sea level and ice altimetry, also generally from satellites or planes. And so it actually turns out today in the volcano module, you'll actually be hearing about the first 5 bullet points that are listed here. Let's see. For every Getsy and also Integrate module, there are 5 guiding principles that all of the modules must achieve. They must sorry, I've got my, address one of the grand challenges facing society, make use of authentic and credible geodesy data, improve students' understanding of the natures and method of science. How do we do science? How is it communicated? Develop student ability to address interdisciplinary problems and apply this learning to social issues in a more deep and authentic way than just volcanoes, they blow up. But in this case, actually thinking about communicating the science to the rest of the population. And increase, in the case of Getsy, increase the capacity to apply quantitative skills. That was one of our principles. So the way the module development and assessment goes forward follows the integrate project method, where you are using backwards design to start with the learning goals, like where do I want my students to get to? What are the more granular outcomes that you need along the way? How would I know if they've gotten to those goals and outcomes? And that helps you determine the assessment strategy. And then you go into the teaching materials and the instructional strategies. Then the materials are piloted and revised before publication. All right. Okay, so I just thought we'd test the controls a little bit. So how about if you go ahead and raise your hand if you already use any geodetic or seismic data in your teaching for any sort. So let's see, we're getting some raised hands there. Woo! So that is exciting. We already have a bunch of people who are already using it to some capacity. So we hope that this module will allow you to go even farther with that potentially. Awesome. So go ahead and unraise your hand. So my controls are a little wonky today. And now how about, just so we can get a little bit of sense of where people are at on their specific knowledge, so he's going to pop up a poll. Andrew will pop up a poll. Which of these methods do you know least about? Oops, looks like we missed seismic on that, but that's okay. We will go ahead and talk about seismic anyhow later. So still seeing some things coming in. All right. In the interest of time, I'll go ahead and end the poll, and it looks like InSAR is the big winner as far as what people know less about. Awesome. Thank you for that. Share results. Okay, did that show? Okay, stop sharing and I'll close it and we will go on. So, quick overview of the different methods that are employed in this module. So we'll start with high precision GPS. This is a station on one of the Aleutian chain volcanoes. GPS is a great entry point for students because they all have GPS receivers in their phones, in their cars, probably in their pockets while you're teaching them. But most of them don't realize how it works and that the GPS is a passive listening device. And that it needs to hear the signal, if you will, from 4 or more satellites, and the time offset from the satellite to the device can solve for the 3D dimensions plus time and give you a solution of where you're at. The way a high precision station looks, you would have this dome probably to protect it. This is the antenna that's listening to the satellites. You have the legs that are drilled into bedrock or sediments. This is connected by a cable to the brains of it, which is the GPS receiver, and also the power and the communication, possibly solar panels. And so if the ground moves, the station moves, and you can measure that. How does this Is this different than commercial consumer grade GPS? Consumer grade GPS is going to stay within sort of the 10-meter accuracy range, which is great if you just need to know what road your car is on. But for the research grade high precision GPS, within just 8 hours, you're down to millimeter scale accuracy in the horizontal and say centimeter in the vertical. And after 24 hours, it's millimeter scale, several millimeters each. And over a couple years of data collection, you can measure changes as little as a millimeter per year. So if we think about how we might use that with a volcano.
One of the things moving magma tends to do is it tends to deform the surface of the Earth. It tends to cause the surface to bulge upward or to spread apart. One of the instruments we use to measure deformation is a tilt meter. A tilt meter measures very subtle changes in the surface of the Earth as magma accumulates beneath the station or moves upward, for example. Another instrument we use is the Global Positioning System, or GPS. So we put several of them out on the volcano. We record signals from satellites orbiting above the Earth, and we look for movement of one of the stations with respect to the other. As the ground deforms, the volcano changes its shape, those stations move, and that tells us something about what's going on beneath the surface.
All right. And so that's in a nutshell how the tilt meters and the GPS stations measure the very minute movement. This picture actually shows us the next method I'm going to mention briefly, which is lidar, the high resolution topography. That works. I think most people are more familiar with this. You can have terrestrial-based scanners, but for volcano work, it's almost always the airborne lidar that is being used. And so you have a laser scanner in a very well-positioned airplane where we're using GPS from the satellites and from the ground in order to know exactly where this airplane is. It's sending down thousands of laser pulses per second, measuring the return times and getting a high-resolution topography. Generally, volcanoes don't have as much vegetation in the areas of interest, but it can sort of, quote, see through the vegetation in a very useful way. So the students use the data, the LiDAR data, to see change, in this case, looking at this big dome development over the course of part of a year between these two LiDAR scenes. So using InSAR to measure volcanic deformation. InSAR is a really powerful tool. It stands for Interferometric Synthetic Aperture Radar. That means interferometric is using wave interference. Synthetic aperture is a method for pretending you have a really big radar antenna by just taking the measurements really often as it slides by. And a radar is the microwave radiation. How it works is that the satellite emits a radar pulse, not straight down like many satellites, but actually at an angle. The radar is backscattered and the satellite measures the amplitude and the phase as it comes back to the satellite. And it's primarily the phase that we're going to talk about now. So phase is a function of the distance from the satellite to the ground. In this case, these satellites are about 780 kilometers up. So that's a lot bigger than the 6 centimeter wavelength of this particular satellite. They tend to range from 3 to 22 centimeters for different InSAR satellites, but it's still going to have a set number of times that you can do that wavelength, between the satellite and your ground of interest, in this case, a volcano. And so if you have a case where there's 2 passes of the satellite and there's no change, this volcano has not changed, so it goes down and the next time, and the phase is exactly the same that is returned to the satellites between these 2 times. If, however, your volcano has actually changed during that time frame, then the first pass, here we go, and the second pass, there'll actually be a difference in the phase. In this case, the volcano has gotten a little bit farther away because it erupted some material out and deflated. So the shift is due to volcanic deformation. So if we want to think about how you actually go about measuring and reading an interferogram, we're going to focus on the upper part of the northern part of the Galapagos Island here, which actually clearly has several volcanoes in it. Interferograms can be a little confusing to read at first, but you want to focus in on the place with the fringes closer together and less of this sort of noise in the other parts. So you want to move from outside of the region of deformation in towards the deformation where you're seeing these repeated fringes. And the first question to ask yourself is, did the surface move up or down? And you always need to check the scale bar of the particular InSAR interferogram you're looking at, because there is unfortunately not an industry standard for colors. But in this case, if it goes from purple to green to red, that is deflation, ground moving away from the satellite. If it's moving from red to green to purple, that is inflation and the ground moving towards the satellite. So in this case, if you come up here and you go purple, green, red, purple, green, red, purple, green, red, deflation. So this is showing you a deflation situation, and you can count the number of repetitions of this fringe. Each one of them is half a wavelength. In this case, it's just under 3 centimeters for each of these repetitions. So if we count them, there's at least 7 of them. We're seeing a deflation here on the order of 0.2 meters, 20, 21 centimeters or so. So that's how you read an interferogram. The last thing I'm going to mention is not geodetic, but it's another important measuring tool that's used with geodetic all the time, and that's seismic monitoring.
Volcanoes, earthquakes serve as an early warning sign for an impending eruption, as well as a marker for the location of moving magma. Volcanic tremor, a long-lasting rhythmic signal associated with magma in motion, can last for minutes or days. Increased shallow seismicity, plus deformation of the surface, monitored by tiltmeter, can indicate an impending eruption. When scientists noticed hundreds of small earthquakes happening around Mount St. Helens, the USGS installed additional seismometers in fall 2004 to monitor activity at the volcano.
So I just want to mention that these animations, along with some other great interviews with volcano monitoring personnel, are part of the teaching materials. The animations were originally made by IRIS and USGS, but they've been integrated into this module. And so now I'm going to stop talking about the methods, and I'm going to stop sharing my screen and pass it over to Katja, who will tell you about the teaching module itself and how to work it successfully with students.
Thanks, Beth. I'm trying to figure out where my PowerPoint went. Here it is. All right. So there we go. Yeah, I'm going to talk a little bit about the module as a whole and the units within that. And this is a photo of my co-author, Rachel Teasdale, and I standing in front of some of what motivated us to create this module. And also hopefully give you an opportunity to kind of play a little bit with some of the data that the students end up playing with within our component. And so I'm just, sorry. Okay. So the module goals, by the end of completing the 4 units, students will be able to interpret geodetic data in the context of monitoring volcanoes in order to assess geologic conditions without direct observation, right? So this idea that we can actually figure out a lot about what's happening inside a volcano without actually going to a volcano. Using the geodetic within the constraints of realistic data sets. So the fact that data are incomplete, that they might contradict each other, and using that sort of ambiguity to still allow students to recognize that they can make forecasts and they can have confidence in some of those forecasting of the activity. In addition, they will be able to identify the risks and hazards associated with different kinds of volcanoes, and then use all of that evidence to create arguments that communicate that monitoring is not just a one-time thing, but it's an ongoing effort. So there are 4 units within this module. The first unit is the renewed activity at Mount St. Helens. So we really examine, sort of introduce students to the idea of geodetic data and how to interpret some of that data in the context of a stratovolcano, and also sort of examine it through potential hazards. Then we move to a shield volcano in Kilauea and model sort of a scientific meeting process where students become experts and analyze data and then forecast a potential eruption. Then we move to Yellowstone, so looking at sort of a caldera-style volcano in which it is ongoing activity, but it does not mean that there's an imminent eruption. So the sort of repeat exposure to a number of these different data types so that students can start to develop some expertise in them. And then lastly, sort of moving away from the entirety of sort of looking at individual data sets, but now thinking about it in that larger context of that sort of societal aspect of not just data, but then also how does that tie into things like sort of value and vulnerability variables and not just the geologic hazards. So some of the strengths of the module is that it's flexible. You can use a unit all on its own rather than all 4. You can do the whole complete module obviously students will have a better, stronger understanding if they do all of the units, but that they can still be extracted as individual units. You can sort of mix it up in terms of what's homework assignments versus in-class, lecture-based activities versus lab-based activities. There are components that are individually based, there are parts that are small groups, and there's other parts that are large group discussion based. But we've tested and piloted this in both very, very large lecture classes and very, very small, so we can say with confidence that it can work in a variety of different types of class settings. And that, you know, this is real data. So it's authentic for the students, and it's in the context of these larger socially relevant problems. So students have access to something that's not just cookbook. And that then they're using that data to make recommendations about societally relevant problems. And of course, because they're doing that, they're also really sort of thinking like scientists. They're reading data as scientists would, they're making observations, they're both qualitative and quantitative, and they're trying to figure out what it means from a geologic standpoint and how that they can build arguments using those data. And then we also ask them to sort of pause and reflect on both sort of what they're learning, but also what's allowing them to learn to kind of have that metacognitive component. So if we kind of take a look at sort of a brief insight into each of the individual units, the first one, as I mentioned, is at Mount St. Helens. And this is from the activity that occurred in 2004. So we have a pre-reading that students can read that gets at some of the history of Mount St. Helens, the 1980 eruption, the hazards that have come from this. And then the initial part of the activity is what we call a gallery walk. And a gallery walk doesn't actually have to involve walking. But what we have are these 3 different posters that introduce students to seismic, GPS, and lidar from the 2004 activity that occurred at Mount St. Helens, ultimately resulting in sort of a USGS alert level. And so a gallery walk is students sort of start in stage 1, where they would actually read a brief blurb and summarize it for their fellow classmates. Then they would rotate and a new group would look at this lidar poster and then look at the data itself. And rather than jump right into interpreting the data, they're actually just describing the data. And then they would rotate again, and a new group would now look at the description of the data. They might potentially edit some of what students have done, so it allows for an iterative process here. And then they move into interpreting the data. And then lastly, they rotate again, and now you have a new group that's now taking the interpretation of the data and determining what would be an alert level. So it's sort of exposing them to all the different types of data while also looking at each other's work and sort of giving feedback to each other in an iterative process. Then from all of that information, they would then assess possible hazards to local populations, local infrastructural issues. And then we actually, we have an interview with Cynthia Gardner from the USGS, who was on the ground as the scientist in charge at Mount St. Helens during this particular event. So she kind of unfolds the sort of what actually happened. And so students can then sort of see sort of how did their predictions and forecasts sort of match up with what actually happened on the ground. These are sort of examples from some of the data from each of the individual posters of the gallery walk. So we have the lidar data that's actually a quantification of some of the visual images you saw when Beth introduced the idea of lidar. There's the seismic data, and there's actually more data than just this. This is sort of the one that is sort of the most complete in that it's the real-time seismic amplitude measurement, or RSAM. And RSAM is actually sort of a quantification of both the magnitude and quantity of earthquakes that occur. So it's sort of a count including magnitude. So it kind of gives you a fuller picture than just sort of individual epicenters, at least for these data. And then the GPS, there's sort of a south-east measurement with sort of a down motion. So students can see, look at all this data. These represent different sort of time frames, mostly focusing on sort of the September to November timeframe. So to get you to sort of think a little bit about what might you do with some of this data, here we have an RSAM, the sort of close-up of the RSAM output. I've sort of put some dates on here. And so we have another poll where we want you to kind of think about, if you were given the opportunity, what would you set as the maximum alert level? So the maximum alert levels are, can we move that poll location? Hopefully you can move it so that you can kind of move it around so you can see the alert level options, normal, advisory, watch, or warning, and then sort of what the descriptions are for those, and then which date. So go ahead and take a moment, sort of look at the data, take a look at the alert levels and see what you would assign as the maximum alert level and when would you assign it. With, of course, the opportunity of having retrospective analysis because you can see all the data. And I can't see the results, so I'm going to let Andrew or Beth decide when it's time to call it.
Okay, I'm gonna say, oh, we're still coming in, so I'll give people a couple more minutes.
Yeah, I mean, there's a lot to be looking at here, so.
Yeah. Okay, I think we'll call it. It's been steady for a little while, so I end the poll and share the results. Can you see them, Katya, or do you need to talk?
I can. Yeah,
Okay.
so I think everyone hopefully can see them. So the majority have selected watch, but we still have sort of good balance on either side of advisory or warning. And then we sort of have the 29th is sort of the winner of the call of when you would call it, but the 2nd of October is also sort of a winner. And so what's really great about this, and this is sort of part of the value of real-time data, is that there's actually no wrong answer here because I mean, there are certain dates when they called different alert levels, but they actually went through every single level of the warning alert system. And it varied with different dates. And so it provides this opportunity for students to kind of see that this is a moving target. It's not necessarily a fixed level that you set an alert level, but that it fluctuates. And again, this sort of gets at this idea that data need to be monitored over time and not just as a single shot, because the value of that long-term monitoring is really valuable so that it provides some context. All right. So the other thing that kind of comes out of these units are sort of that societally relevant, as Beth described, sort of one of the key takeaways for sort of Getsy as a program. So as we just mentioned in Mount St. Helens, we kind of look at which regions are impacted by hazards. In the Kilauea unit, we have the opportunity to kind of look at not just the hazards, but also sort of the potential cultural sensitivities to proposals of diverting lava. And so we actually have some videos from, and these are sort of 2 screenshots from the video of a town hall meeting that was occurring during a period of time when there was lava that was potentially threatening the town of Pahoa. And there were different residents of the area that were speaking about their concerns about the lava. And there was somebody who was both a native Hawaiian who was talking about sort of the philosophy of sort of from a native Hawaiian perspective and sort of thinking about it through the eyes of Pele, versus someone who is a non-native Hawaiian and sort of thinking about the idea of sort of arguing for the idea of diverting lava. And sort of getting students to think about beyond just the idea of the science behind it, but also some of the sort of that there's more to it and that it's in the context of the larger social context that we're thinking about geology. In Unit 3, we take a look at Yellowstone has sort of so much hype around, there's so much misinformation about the idea that it might blow any day. So we really wanted to try and address that by having them think about how would they talk to a friend about how do you communicate that even though it's active, it's not actually going to explode. And then in Unit 4, we really kind of take that full synthesis of looking at not just the data, but also the socioeconomic, infrastructural, corruptive levels of different locations to really kind of think about how do we think about risk. So in Unit 2, as I mentioned, we do get to sort of this idea as a pros and cons of lava diversion. But before that, we sort of just talk about lava flow hazards. So now we're sort of focusing on different kind of volcano, letting students recognize that, you know, volcanoes have different kinds of hazards. And they do this through the context of what's called a jigsaw. And a jigsaw is where you have different groups become experts in one particular type of data. So in this case, we have a group that becomes an expert in seismic data, a group that becomes an expert in GPS, a group on InSAR, and a group on tilt. And so the seismic and GPS, they've already been exposed to. So one of the advantages here is that we're building knowledge from something that they've gotten exposed to before. So we're adding some new information, but also building on some others. So here's examples of data from each of the different expert groups. So you can see the GPS data and the sort of dates along here. So you can see sort of a clear change in the GPS data, the tilt data around the same date. You can see a clear change in the tilt data, the seismic data, again, sort of right around the same date, we see a significant shift in the RSAM. And then in the InSAR, it's a little bit more nuanced because we have a deflation in one location while it's sort of leading up to the event of all of the tilting GPS and seismic. So it also helps them recognize how time plays a variable in which data set is going to be valuable for a larger time frame of being able to observe and understand a volcano. And that not all data are going to be instantaneous in the moment of the activity. The unit, sorry, I'm just trying to figure out if there's something else. I think that's what I want to say. Sorry. Okay. So unit 3 is, as I mentioned, about Yellowstone. So students are introduced to this in the context of mean recurrence intervals. So they actually get a little bit of practice doing some mean recurrence intervals and also look at seismic swarms. And then in the class, they then look at, we break them up into different groups. So students look at seismic swarm data by decade and then report out to the whole class. And so as a class, kind of calculate a larger mean recurrence interval for seismic activity in Yellowstone. So they can start to see that there's sort of this regular activity of seismic activity within Yellowstone. It's sometimes been described as sort of almost breathing. My co-author Rachel Teasdale doesn't like that analogy, but I do. We then compare swarms to the GPS activity in the region as well as InSAR data just within one decade, just to kind of not make it too messy, but allowing them to see that there's other activity that's happening, but they're not necessarily correlating with when the swarm activity is. And so it's not, you know, even though we can kind of look at individual pieces of data and see that there's activity, it doesn't mean that as a whole, all of the Yellowstone is preparing to erupt. And so that's sort of ending with sort of thinking about how would you respond to a friend that's convinced that Yellowstone is about to erupt. So to kind of think about that, when we talk about seismic swarms, we can kind of think about it as a definition of a significant increase relative to the background amount of seismic activity. And so on this particular graph, so this is the decade of 2000 to 2009, take a moment and see if you can identify how many seismic swarms you think there are in this decade. So hopefully a poll will pop up and you can kind of take a look at the data and see what you think. I'm assuming everybody else can move their poll box so they can look at the data.
Yes.
Okay.
That works. Okay, I think we have almost 40 votes in, so I'm going to end the poll. And the winner is 5. People are choosing 5 swarms, also some 4s and a couple 3s.
So excellent. So we have 5 votes, and what we sort of came up with was 4. And you know, and that sort of, again, this is the idea that data are messy. It could easily, this is a rich opportunity for discussion in the class. So the reason we identified 4 is because this is where you see these significant spikes of sort of over more than 100 within a sort of given period of time. And so, and this is sort of that sort of significant amount above the background. Now, there's definitely sort of, you could argue potentially that there's another swarm in here. You could argue that there's another swarm in here. So I think that up to 6 is sort of certainly potentially a discussion, and that's something that you could decide as a class that's how you'd want to sort of assess your definition. But we sort of look at the sort of steepness of the slope change and sort of how many are sort of over and above that background. So again, this is sort of one of these things where the fact that not everybody gets the same answer actually leads to more positive learning opportunities in the classroom environment. So sort of one of the benefits of working with real data is that it is messy. And so as a result, it leads to some really rich conversations and discussions and learning opportunities for the students. So in Unit 4, we don't necessarily look at the data from any one of these individual volcanoes, but what we do is have them look at how much data are available for a particular volcano. So our 3 volcanoes, Mauna Loa, Fuego, and Rinjani. So Rinjani is in Indonesia. Fuego is, oh gosh, I just had a total blank.
Guatemala.
Thank you. In Guatemala, and Mauna Loa, of course, is in Hawaii. And sort of looking at these different contexts of not just what kind of data are available. So what are the hazards of, so really looking at the geology, what are the hazards? What are the, what type of hazards would it be? How fast moving are these types of hazards? So the introduction ahead of time is to this idea of volcanic explosivity index, and that different volcanoes have different levels of explosivity and hazards associated with them. How frequently do these volcanoes erupt, right? So these different geologic factors, but then also looking at the sort of notion that there's a value to how densely populated is the region, and what kinds of infrastructural aspects, vulnerabilities might there be? So are there bridges that could be knocked out? Are there major reliance on highways that would, sort of shift how people evacuated? Thinking about socioeconomic status. So how many resources does a country have to be able to respond to a potential hazard? And the corruption index is a numerical device that looks at how corrupt different countries are to sort of determine the higher the corruption, the more likely the impact would be exacerbated in terms of a potential hazard or a risk. And so, so the idea is we're not necessarily having them calculate a number value, but looking at it from a sort of holistic of which one would be the highest risk, which one would be a middle risk, and which one would be the lowest risk. And so individual groups look at one volcano and then they sort of remix it up. And again, this is sort of one of those places where you could mix it up in terms of, you could make it, the whole class could look at the data. You could have different sections of the class and do it sort of as a jigsaw. You could do it as sort of like a think, pair, share. There's a number of different kinds of ways that you could sort of mix this up. But the final sort of outcome is to sort of think about how would you then convey this information to a non-expert through the idea of writing a letter to a political official about the need for ongoing monitoring of volcanoes. And this is one that really kind of then wraps up sort of allowing them to really appreciate that value of monitoring in an ongoing basis. So there might be some challenges you're anticipating that could potentially occur within your classroom. Sort of sometimes sort of thinking about it from the standpoint of like, well, I can't cover the sort of volcano content I need because I'm doing all this other stuff. And yet if you sort of think about the lessons as a whole, a lot of the things that typically get covered within a volcanic unit, like different types of volcanoes, the types of hazards associated, the different explosivity of different kinds of volcanoes, ultimately get covered within this, but it's in the context now of something that's societally relevant, that's authentic for the students. And so it makes it more meaningful for them rather than just learning a bunch of facts. Students can get overwhelmed. There's a lot of information. There's a lot of different things, moving parts. And so I think, it's sort of important to think about that it could be broken up, right? One, we sort of talked about the idea that you could do individual units, but you can also sort of think about in both Unit 1 and Unit 2, we sort of have options for different class lengths. So there's sort of a 2 50-minute class or a modification that makes it just for 1 50-minute kind of lecture class. And the same goes for Unit 1 in terms of a 75-minute versus a 50-minute. So there are certainly options. You can think about some things. Unit 4 could actually be a homework assignment rather than an in-class activity. You could have some things be lab. Unit 2, the jigsaw activity works its well, sort of lends itself nicely for a lab activity. So there's definitely ways that you can kind of break this up so that it gets a little bit less overwhelming for students. Grading, always, I should have had that as challenge number 1. Grading, one thing we've done is for exam questions in the assessment, we provide options. So this is a stratovolcano in Alaska, but we have them looking at GPS data from it. And so in this case, this particular exam question would be actually drawing on the map and interpreting the data and writing out their answers. But we've also created options where the multiple choice options are already created for you. So you could either do it as a multiple choice, or you can do it as open-ended depending on sort of what your preference is and what you think students would best respond to and what your reality is for your own context. The questions that we have in class as part of the activity are reflective, but they don't require grading. But what's nice is that they inspire class discussion. So some of which we've already sort of talked about, but here's sort of an example from the end of Unit 1, sort of asking them which parts of the activity were most helpful in making them confident about assigning alert levels, and then sort of identifying that as strategies that they can potentially use in future activities, since they do sort of build on each other. So getting them to both think about the content, but then think metacognitively about their own learning approach. In some of our longer assignments, so things like writing to the senator, or in this case, is sort of a little volcano bulletin about what, you know, sort of for a non-expert audience. We've created rubrics that sort of allow for you to make it a sort of a quick checklist. I actually converted my rubric into my online learning management system, so my Canvas site. And so then I was able to just quickly push buttons and be able to make the grading go very quickly. And so I had students submit it digitally. In addition, we've tried to create the handouts for students as an option that have sort of this idea of a TILT framework, and a TILT framework, the Transparency in Learning and Teaching, that's an equity framework that allows students to more easily understand what it is that's being asked of them, so that then they're more likely to actually know exactly what to do for a particular assignment, which tends to mean fewer questions for you. And so we've set it up as sort of what's the purpose of the assignment, what's the task specific to this particular assignment, and then how do they know whether they're successful or not, their criteria for success. So it's modified from the original TILT framework. If you're curious about that, I encourage you to sort of check out that website, tilthighered.com. They've got a bunch of resources. But we've tried to create it in that framework so that then that's something you can hand out to the students as well. And that allows them to better sort of understand exactly what's being asked of them. Another concern might come up in terms of, certainly, you know, my interest students personally have a lot of range in terms of their access, their previous experiences with analyzing data and graphs. I have a lot of students that are kind of math phobic in my intro classes. And so we really try to make sure we scaffolded these processes and sort of data analysis within the individual units. So for example, in the gallery walk, we prompt students to examine the pieces of the data before really interpreting the data. So kind of getting in that practice of how to look at data and how to think about data. And then in Unit 2, there are videos and readings built into it so that there's multiple ways of accessing that information. I have actually, in the Jigsaw activity, I've broken up groups by assigning them. And so I will make sure that, since InSAR is one of the new methods, I assign that to one of my stronger groups of students, so that then I sort of know that I can have a little bit more confidence that they're going to be able to navigate some of that slightly more technical content. But they get re-exposed to InSAR then in the next class period. So that the idea is that they're constantly getting more and more exposure to it, so they're gaining more and more confidence with it. In addition, as you've sort of seen from how we've analyzed data, a lot of the assessments are open-ended. So there are wrong answers, but there's also a lot of freedom for multiple interpretations as long as it can be justified using data, which might have students feel initially uncomfortable. But I think that if you really explicitly indicate for the students, like, this is a great thing, right? So this is both a challenge of science, but one of the benefits of science is that we have ways of sort of thinking about creatively, how do we interpret some of these data? And then the fact that those are some challenges, the real reality and the authenticity of working with real data. Beth, do you want to?
Yeah, I think there's time. Do you want to hand over the sharing to me again?
Yes.
So unshare.
Yep.
And I will share. Okay. And then, all right. So I just wanted to give people a chance to actually see what the what it looks like and see some of the components as it would be on the website. Maybe some of you already looked at it, but here's the front page to Getsy, the circ.carleton.edu/Getsy. And so you can see we have intro level modules, majors level modules, and we have 2 field oriented majors level modules. And so here's our volcano one here. Thinking about it. And so if you're familiar with other Getsy modules or integrate modules, this will look extremely familiar to you, but the front page walks through the table of contents, some of the strengths that Katya has just been telling you about. And there's a more detailed table of contents that goes over the module goals and each of the different units. And then you have the different units themselves, in this case 4. And there's also a page that you can send the students directly to, which it looks like didn't get linked in. We just put it up on the front page recently, but this will be up by later today. And there's an assessment page for the actual exam or take-home project type of questions in a summative fashion, and instructor stories of how it was taught in Kutch's class, in a community college, in Daniel's class, in an R1, in Rachel's class, in a comprehensive university, just so that you can see what it would be like in different settings. And within a given unit, there's the same overall format where it talks about the learning outcomes, what the course is that you might have it in, course or courses, and then all of the different files associated with it and the different sections. And then when you get down to the bottom, a couple tips on the mechanics of it, the pedagogy, and I have to say they are super detailed and have lots of information, even more than many of the modules. And how will you know the assessment? How will you know if the students have achieved their results? And then some follow-up references. So this is the same format that you would see in any of these Getsy or Integrate modules. And these pages are intended for the authors, and then or sorry, not the authors, excuse me, for the instructors, and then provide the materials that you would then give to the students as well. So now I'm going to switch. Oh, it looks like my chat box disappeared, but if anybody is coming up with any questions, feel free to put them in the chat box. We'll go back to the PowerPoint and sort of more formalize the sort of reflection and discussion. So you've heard us talking now for about 45 minutes. And so at this point, we'd love to get any questions or comments on your side. So questions for Katja about what it's like to teach the module, or questions for me about the methods, the geodetic or seismic methods, or how they're applied. So feel free to put any questions that you have into the chat box. We'll give people a little time for that. Do any of the modules use real-time data, seismic, geodetic, or otherwise? No, none of the modules the teaching materials that are provided are not pointing to the data portals and saying, here, students, go to the data portals and pull back the data yourself. However, we do provide the links, and those things are often in the references. So if anybody really wanted to have that part with their students, you would be able to do it, but that's not what is in the not what's in the module itself, primarily because the main emphasis is more intro level, although certainly it can be and has been used in sort of the beginning of a more majors level volcanology course as well. Did you want to add anything to that related to the data?
Yeah, so one thing that I mean, it's sort of, I saw that was Eric, who I know lives in the Pacific Northwest as well. And so that's sort of one thing that's actually been kind of cool is for me to be able to show, so they looked at, Mount St. Helens data and then pull up the data that's sort of real time on the Pacific Northwest seismic network and allow them to see sort of what's the current seismic activity in each of the different volcanoes in the Pacific Northwest. And sort of see that since I live in Bellingham, Washington, which is near Mount Baker, there is one seismograph on the mountain, and let them start to realize the reality of sort of what's being under monitored. And so it gives them an opportunity to also sort of appreciate sort of the value of monitoring equipment and how well monitored Mount St. Helens is and how under monitored other volcanoes are, but also the rationale for why. I see a bunch of questions about online.
Yeah, do you want to field that at all?
So I think, yeah, I mean, I do think that it's a lot of, because sort of there'll be, it would require probably some work to get it to an online format, but I do think that it could lend itself, particularly, I mean, I think that, you know, sort of there are strategies. I've done sort of online activities where students end up engaging in different expert group work. So something like a jigsaw or a gallery walk, where they have to look at individual information and then post it to sort of like a Google Docs kind of document, where then it becomes crowdsourced because people are all adding information to a particular, you can assign discussion groups within some of the online modules, online platforms. And so then students would sort of have to communicate with each other and navigate through some of that. The readings and the videos themselves, because they're sort of embedded within some of the reading assignments, would actually work nicely on an online, because then they can kind of click on the video and they can, you know, so some of that actually would work well for an online. But I won't lie to say that it would be an automatic easy to do. I don't think, I saw somebody ask if Unit 4 would work best for online instruction, and I don't know if that's true, because Unit 4 really sort of relies on them understanding what some of those other methods are. So they need to at least have some understanding of what geodetic monitoring is in order to be able to understand what those things are. So at least there'd have to be some background information on that sort of, and there are links and there are resources to help students be able to get there. So it'd be doable, but it's, yes, Unit 4 is different from the first 3 in terms of some of that sort of more quantitative assessment in the previous 3.
There's another question there. I think this would be good for you, Katja. What are effective hooks that you use to introduce and entice students to look at what might otherwise be considered, you know, boring and tedious data?
Yeah, so I'm trying to, so I think for, I mean, it helps that volcanoes are kind of sexy topics. Just in, you know, sort of students are kind of excited to talk about volcanoes anyway, but, and so I think trying to provide some context as to why this might be data that are worth looking at. So we have sort of a, we have one brainstorm ways that they might try and figure out whether a volcano is going to erupt or not. And so they kind of do an individual brainstorm, and then they sort of talk to their neighbors, and then we do sort of a share out as a class. So it gets them starting to think about that. And then we sort of say, well, there's ways we can quantify that. So it gives them a way of sort of starting from their prior knowledge, building on that, and then moving into the pathways of what do these data look like. I think it's not so much that students don't want to look at the data. I think they sometimes get frustrated because it is not super easy to interpret all the time. And so I think that that's the part that is more what I find that I need to kind of prepare my students for, that, you know, data are messy and sometimes they don't always give us a very obvious answer. And so trying to think about how do you frame that in a positive way, rather than think about like, yeah, that's a real bummer, but rather think about how challenging this is and why it's so important that we have multiple perspectives coming to this, and thinking about how we want to make sure people can kind of interpret from multiple directions, but also why we have multiple sets of data and how important all those data are. So trying to really sort of build up the positivity of that ambiguity.
Let's see.
I do see somebody here says, do you have data sets showing how parameters change before previous eruptions? So that's in the Mount St. Helens unit, we have them. So they look at the seismic activity from 2004, and then we follow up with having them look at seismic data from the sort of previous decades, starting in, you know, sort of 1980 timeframe. And so it affords them the opportunity to then contextualize how that 2004 event. So then they start to dial it back a little, like, oh, it's not as big of a deal as we thought it might be, right? So it sort of allows them to sort of see how does that fit in the context.
Another question is, do we have to teach all 4 units, or we could just use 1 unit if constrained by time? Absolutely. You know, I think Katja can save you more. I mean, you could get a lot out of, you know, either unit 1 or 2, probably, you know, as a starting point. They would not go as far towards the understanding of risk and vulnerability, but they definitely would, all of the units have some element of societal hook component too. So they're definitely possible to do just 1 or 2.
Yeah, absolutely.
One question came into me privately, but I think it's a good one. So as I understand, you're coming at this from a geodetic perspective, but is there no incorporation of other monitoring methods like gas? And no, not that we don't like gas emissions, but like we had to stop somewhere, you know. So I there are other teaching materials out there that would allow, for instance, to bring gas emissions from Yellowstone in sort of on your own manually, if you would. But for this point, we had to sort of cap the number of data sets we were looking at. And some of these, like InSAR, are very not represented in other teaching resources. And so we wanted to get some newer things out there. But we realized we were not comprehensive.
Right, and I
also
think
repeat photographs and other things like that are also super valuable.
Right, and I think it's also sort of, that's where I mean, I sort of saw there was a question about upper level students. One, yes, I think upper level students could tackle module 4 as a homework. If they hadn't done the other 3, it might still help to give them some sort of intro foray into sort of what different methods are for monitoring volcanoes if they're not already familiar with that. But from the question of gas, and that would be a great way to sort of leverage this for a upper sort of 300 level class, is maybe thinking about then having students find data and bring more data in from something, and that sort of leads to a richer discussion.
All right, I think we got through the questions that have come in. So I meant to mention this at the beginning and I totally spaced on it, but we like to encourage people, you know, I know you can come to a webinar and like get some ideas and then not actually think through to like, what steps would I need to take in order to use this myself. So I'm just going to encourage you at this point to take a few minutes to jot down your ideas for your own teaching, like which unit or units might be most likely to use, you know, what might you need to change, you know, so just jot a few things down just to yourself, whatever you like, paper or digital, before you go on to the next thing. And we'll be happy to stay on, you know, a few minutes longer if any more questions came up. We'll also ask Andrew just put up the webinar survey link. If you could take a few minutes to give us a little feedback, that would be great. He'll also send it out in an email, and in a few days, the recording and the PowerPoint will go up on the webinar page for this webinar. Anything else, Katja or Andrew? Oh, yep, and then I need to also just mention the next so hopefully people can be jotting down some ideas, and then I'll go on to the next part of the NAGT series. So the next GETSI webinar will be in a month, and that will be about teaching about the water cycle with data-rich water resource activities. But that's not until the end of February, and next week is a very cool webinar coming from the on-ramps, tectonic on-ramps, which goes through a series of quick entry start guides to effective active learning strategies that maybe you haven't been brave enough to start yet, but this will help you think about jumping into more active strategies. So you can always find out more about the schedule at the NAGT webinar webpage. Thank you so much for your time.